Hi, this is Bill Foote, and it's second round of trying to figure out what to do with conditional probabilities and so on. The do's and don'ts, we ask the question, what is the plausibility of a decision in that given data? And the do there was to place decisions in a column along this side. And if we look at that, it looks like this over here, this mess. There's a due decision, D and not D. They're decision alternatives. And this is kind of like a primitive model kind of decision. It's a two action, two state of the world decision model. And it's really a risk model, not an uncertainty model, because the decision outcomes are known with probability. We are mashing together the number of times that a state of the world occurs. That state might be accept, might be rain. It might be I wear a tie to class. I don't wear a tie to class. I wear my reading glasses. I don't read my reading glasses. Or any number of states and state and decisions as well. But there has to be at least two. One that's for, one that's against, a 1 and a 0. Same with the decision and the decision outcome. Notice where we're putting the decision. We're looking at the number of decisions that are coincident with, conjuncted with the number of states. It's the condition decision D equals true when state S equals true. There are 5 in this particular example. But we look at both decisions across the one state in order to answer the question, what is the plausibility of D? Well, states can occur 8 times, and D's participation in the 8 times is 5 times. So the relative number is our plausibility index probability, and that will be 5/8. Okay, enough said about that. Okay, now we're going to do it all for Bayes. Yes, everything is for Bayes here. So let me set this up. We just said that the probability, there we go. The probability of D given S equals 5/8. Now, what was the 5? What was the 8? They were, in symbols, the number of ways associated with the probability of D and S, which, by the way, is the same as S and D. They are symmetrical. Per the probability of S. Now, if we multiply both sides by the probability of S, we see that the probability of D given S times the probability of S equals probability of D or not or, and writing the A, saying the or, dyslexic. Okay, need more sleep, Bill. There we go. Is equal to that. Now it is also true, go back over here, that if we do the thing that we said we won't do to answer that question, we can go along the row and look at S in the circle, the 5 times there, as the number of times relative to D. Conjunction again, both and. The probability of S given D in this case is 5/7. 5/7. 5/7. Now, that means that, and then out of 16, we can convert all of these to probabilities. We would say that the probability of D, all of the ways D can evolve, S and not S, is equal to 7/16. And the probability of S given D, by analogy, with the way we did it over here, by analogy, and just think analogically for a second, will be equal to, now let me go back to the equation up here. This will be the same as, remember, this was 5/16. It's the same as, just by analogy, probability S given D, probability of D. Now, the way we used to think about this is that no mathematical proof required, right? Just mnemonics, because I get confused. I get confused all the time by this. I have something in my mind all the time, and that's a grid. I do the same thing all the time. It's basically a numerical integration, but it is a grid to compute these probabilities. But notice, it's the same thing, symmetrical, both sides. Okay. Now, if this is true, and we divide both sides by P R S, the probability of seeing the data, means we got to divide it all the way straight through. We now have Bayes' rule. Bayes' rule says, let's do that first. Anything divided by itself is 1. 1 times anything is itself. Ooh, okay, then we get this ratio of PRD over PRS. So PRD is what we call a prior. Before we see the data, which is S here in this case, before we see the data, we have an idea about how the decision might work. It might be from experience. And the experience might be, and this is of the entire community, not really subjective. It is backward looking, as Soren Kierkegaard would say. Look backward for, he did this in one of his journals in the 1830s, look backward for understanding, but look forward for what? Making a decision or living. Probability of D looking backward. Okay. And then we make data happen. Okay. We observe data. We observe it's raining out or it's not raining. We observe the number of people in the open air market. The labor market down the street. We figure out what is the rate of exchange of rupees for one, this is what we do. Okay, we make observations. But before that, we think about what might happen based upon what has happened. That's PRD. PRS, however, is the probability of the data happening. And it's a tad more complicated. Yes, it is. But for us, it's not so complicated. And we'll come up with a way of dealing with it. But what we have in the end here is, get rid of this. Is what we're going to call Bayes' rule. Give myself a little bit more real estate here. It ends up that this is Bayes' rule. And it's also the law of inverse probability. Used, over almost 100 years, and then we lost it. Really because of computational issues, but also because of the influence of a particular way of looking at how we make any kind of inference. I'm not going to get into that study. A fascinating study because it's happening right now. So it's a ratio of two things. Now remember what's in the top here. This is the joint probability of S and D. Well, this doesn't want to work so much. Which is the same as D and S. That's what is in the numerator. Now, it turns out that this is 5/16 in my example, our example now, and this is 8/16. Get in there. 5/16 divided by 8/16 gives us 5/8. Bayes rule. Now, that is the rest of the story. That is the rest of the story. And we can tell more story with an example from Richard McElreath. And we're going to tell that story right here and right now. Let's set that up. So all of this comes from the classic signal detection problem. Now, it's in Richard's book, Statistical Rethinking. Look it up. Don't have the page number for you at this moment, but it is in this, and this is a formal citation. Richard McElreath. It's the second edition, and it's in a section that I just can't find it. Okay, no problem there. It's in a section in a box. So, signal detection. We don't know what's going to happen, and we'll call that H. Those are our decisions. Either happens, doesn't happen. Now he's using hypotheses here. So same idea, same idea. Okay. So we have that set up. Binary state. We then observe Q that says D occurs or D doesn't occur. And that Q, we'll call that S. Okay. We see a Q. It's data. And then we're going to deduce something. The first thing that we're going to say is if D is true, if that's a true statement, probability is really low, 1% of the time. And this could be a hypothesis, remember. Okay. It's just like radar operators actually see the thing under the sea or in the air, or it's a flock of birds as opposed to something else approaching. Like starlings over Rome. Check that out. Starlings once a year, and I think it's happening right now. It looks like static. So many starlings. I did detect the one red woodpecker in there. There is one. So this is 1%. Now, this is often called the base rate. And we're talking about scientific innovation leading to commercial innovation. This would basically say that 1 in 100 new products launched, it might be a launch, will make it. Okay. Now, out of all of the ones that were thought about, one will make it. I don't think that's unreasonable. Out of all the ones that were thought about and then actually launched, and then we actually see what happens in the universe, it might be a lot more than that. Okay. Well, that's kind of where we're going. And another thing is that the probability that S occurs, given that D is true, is set to 95%. Now, this is recommendation of one Ronald A. Not recommendation, probably example is better, but everybody took it after they read them and said, "Oh, we got to use it because the master said so." And yes, he's a master, absolutely, guy's brilliant, unbelievably brilliant, and created something based basically on everything has the normal distribution. Kind of an interesting idea, but his ideas live on today. And we have to know what to pick and leave the rest. Okay, 95. The probability then, see if I can do this without messing up my nice screen here. Okay, the probability then of S, of seeing that state of the world, that Q, if D is false or not D, is 1 minus 0.95 is 5%. Now, those of you who have been through hypothesis testing in the now conventional frequentist tradition will recognize this. This is a significant test, the idea of significance. And the first is called a base rate, and it's hardly ever applied to this analysis that we would have learned in most stats courses, the ones that I learned, certainly. Although I've got this weird hybrid background. This is called the power of the statistical test. And 5% is called the false positive rate. Okay. Let's see if I can get this to work. Oh, no, it won't. There we go. Now this is over. In probability, and we're probabilists here, we're saying that 5% of the time, If D is false, our hypothesis is false, or a decision is the alternative, um, then we will see S. Me, I don't care, but a lot of people do care. False positive rate. And we've been schooled in this with recent pandemics that I get a positive test, but it was in this range of 5%. And I'm not really positive. That's why we have 3 tests or 4 tests or multiple kinds of tests, different models. Very quite expensive to do. False positive rate. Okay, let me move this over a little bit. And of course, we have our Bayes formula over here, which is where we're going to dump all of this in. We want to find out the probability that B is true, our hypothesis is true, that our decision's good, given that we see an observation. Okay, S, state of the world. Yeah, given that. Okay, that's what we want to find out. How often are we right, given that data? And we have 3 terms. Term number 1, 2, 3. Now, the probability of S is probably problematic. But we're going to have a couple ways of doing that. One way is over. That's a nice upside down trapezoid. We need a bunch of things here. One thing we need is this thing to work. All right, there it goes. We need the numerator. And that's pretty easy here. It's 0.95 times 0.01. Now we know something about this already. We know that when you multiply those 2 things together, this is just the joint probability of S and D, right? We know that. And if we look at this, it'll be 0.095. Okay, that's what that will compute to. Okay. Down here. How do I know that? I move the decimal place over twice. Okay, that's the rule, but that helps myself. Okay, so we have the numerator. Now the denominator. Let's just look at what the denominator might be. Way over here. Do it for Bayes. Yes. All right. Oh my gosh, what a mess this is. But look at this. The denominator of 8/16. How did we get that? Well, one way you can get it, we need D and S. D and S. S and D. S and D. Okay, we need to get the 5/16 and the 3/16 somehow. Those are joint probabilities. Well, we just saw that if you take the likelihood, which is 95%, and multiplied it times the equivalent of 7/16 here, okay, fair. Different numbers, I know. You can get this probability of D or S, and you get the other probability of D over S. You can add them up and get the right answer. Yes, you can add them up. Okay. I'm going to use that. But to use that, let me just put this over back here in the framework. Okay. This is the algebraic way of looking at things. Okay. To use this, we can take advantage of this, where we have D dot D. We have S. We have this 0.95, 0.05, which are what we call the likelihoods. I didn't say you wouldn't cry through this whole thing. Yeah, a little bit. All right. Okay. Now, what else do we have? We also have the probability in the margin. We have the probability of D, which is 0.01. And the probability of not D is the rest, 0.99. Okay, those are our priors. Well, why is that happening? I have no idea. Okay, you have an idea. No? Okay. I love the technology. They switched out the Microsoft whiteboard for this new version. I just use D for decision, either decision, or against, true, false. Okay, either way you want to look at it. Now, if you multiply this 95 times 0.01, like we just did up there, you get the joint probability of the D's and the S's. Okay, so that gives us that. And if you multiply the 0.05 times 0.99, get 0. I already worked this out. You cannot do this in my head. I don't even want to try. And if you add them up, you get what is 0, 99 is 18 and 9. Get roughly 5%. Just above, just a little bit above that rate intuitively. The thing called the false positive rate. Now, this is the probability, though, of seeing the data in our other model there, okay? Seeing S, the signal, the test. Right? Given the test, okay, and this might be a test market, it might be a test prick on the end of your thumb or blood, it could be anything. Okay, it could be just taking a look. That's the whole problem. We're just taking a look. And now we're taking a look and we're thinking about it. Knowing is not just taking a look. Oh, blood, therefore, oh, I don't know, it might have come from somewhere. So it happens to be red, but that's just not enough. Okay, now we have our denominator. Oh, yeah, there's a formula for that. It's our S given D times PRD, PRS given not D times 1 minus PRD. Okay, that's what it is. It's a weighted average. Probabilities, maybe 0.059. And the rule will therefore say probability of seeing a test and the probability of plausibility of that decision is the ratio of these two. Joint probability divided by the probability of seeing all of the data, one relative to the other. It's the 5/8 in the other example. Exactly that. Okay. And it's a little over 16%. Now, change these numbers, make the base rate really high. So if you make the base rate really high, what would this look like 50-50? Okay. If you think that everything you do is going to work out wonderfully all the time, so, or at least at a flip of the coin, here it only happens once in 100. Okay. And a lot of entrepreneurial shops actually operate this way because they know this to be the truth. Out of every 100 ideas, one will work. Well, what if it's out of, if they know we're going to make every 10 ideas that we generate, because it's costly generating ideas and showing them, improving them, and so on. Look at FDA four-stage trials. This is where all of this comes in. That 16 doesn't budge a lot. Okay. I wish I had better odds for you for your success. 16% of the time you will be successful given that test. Okay. And that's the true rate that you end up seeing and now being reported in a lot of tests. Yeah, it's around 15-16%. They'll go 85% of the time, but the other 15, you're going to get the wrong answer. Okay. So this is McElreath's example. Well, I did happen to find it. It's on page 51. There we go. At the bottom. Gray block, where this example comes up. But he also refers you back to the very end of the book, which is chapter 17, and that's horoscopes. And the first sentence is indicative of his tongue in cheek, but he means it, and I mean it too. Statistics courses and books, this one included, tend to resemble horoscopes. There are two senses to this resemblance. First, in order to remain plausibly correct, they must remain tremendously vague. Okay, ounce. Okay, figure that out. Second, there are strong incentives for both astrologers and statisticians to exaggerate the power and importance of their advice. And I put myself in that same league because I'm an economist by trade, and I have seen this over and over and over again. What this framework allows me to do is to have a principled conversation with somebody about a complicated issue. That's what it allows me to do. It allows me to abstract. No, it tells me, given all of the assumptions, what's plausible or what's not plausible. What actually happens will wander all the way around that. That is the word errare, which we get our word error. It's a wandering. Okay? Particularities don't match our models. If they do, I go like, that's not something, I don't think I got that right. If they widely diverge from our models, we don't probably have it right either. We don't have a good account of those things that are wandering around, which are actual outcomes. So let's keep that in mind. The example he gives of the messy history of the history of science and the history of discovery is equal parts wonder and blunder. Uh, a lot of people who are highly esteemed, very, very good researchers make mistakes, errors, wandering in judgment. I did just recently in front of a class. And that's why we have to do these things together. And the business of peer review has to be not just independent, but there has to be a lot of pre-publication of results thought about. Here's a framework for us to begin to have that kind of a conversation. We almost never hear about all of the results that didn't work, the dead ends and the blind alleys. And sometimes they go off a cliff. Those people are typically fired, not producing enough on time, in full. Well, actually, they actually produce the knowledge that says you can't go in this direction, you must try a different direction. Let's redesign things. Now, the other aspect of this, especially for us, of course, like the strategic decision analytics, is that frameworks like this are very nice. There's a lot of assumptions. This framework does not handle uncertainty. It just doesn't do that. Game theory tends to go in that direction. This seems to handle risk and how believable, how credible are any of these numbers in the first place. That is the prior. That's what the prior says. How believable, how credible. Here, the hypothesis that it's true, not very credible, only 1%. The rest of the time, blind alleys, dead ends. Good knowledge, we call it inverse insight. But having said that, the research lab that only produces inverse insights doesn't last very long. Doesn't capture the imagination of investors, unfortunately, and it does take money. So we do have constraints, hard constraints and soft constraints that we will need to look at to build on this model. Finally, the stuff that happens in economics happens only once. It's a sample size of one. Even though we get a sample of prices, each one of those represents unique particularity in space and time and with people doing all sorts of things in their lives. It only happens once. An experiment with an observation of one. And we have to keep that in mind at all times. Decisions, write the check, it happens. And we often say, well, if it's a bad outcome, the decision must have been bad. No, the decision wasn't necessarily bad. That is a logical fallacy called post hoc propter hoc. And it's something we need to build into our callousing, emotional callousing, as we build more and more objectivity, which we will do. And I will leave you with that really long diatribe based upon Chapter 17 of Statistical Rethinking and page 51, which is where this example comes from. My own observations are my own, and my errors are certainly my own, but I know a lot of people. Well, we have to admit our errors, don't we? We'd better. I'll leave you with that. And again, this is part 2 of 2 videos. This is the longer of the 2. And I think the more interesting of the 2. But you will see it And again, my thanks go out to Camilla, who pointed this out in class. That takes some guts. That's good. Courage, mes amis. Have a great weekend. Thanks again for your kind attention.